Why is this computer playing America the Beautiful as it scans this graph full of peaks and valleys? And why was that note so sour? The computer is actually analyzing someone's health in a lab at Michigan State University. The squiggly line on the chart records the levels of a number of important substances in a person's urine. If a peak is too high or a valley is too low, it could mean trouble. These graphs are helpful, but they're also hard to read. It takes a trained eye and a lot of patience to check every result in one of these charts. The reason is that people are not all alike. There is no single normal value for a substance like sugar in a person's urine. Instead, there's a distribution of values for healthy people and a different distribution for each compound. These distributions tend to be quite symmetric, so we can measure their center with the mean. But the distributions differ a lot in their spread. The level of some compounds doesn't vary much among healthy individuals. A reading far from the mean for this compound, therefore, could signal illness. But the concentration of other compounds varies a lot, so a value quite far from the mean might still be normal. Clearly, what would be helpful here is a numerical way to describe the spread of these distributions. In this unit, we'll learn about the standard deviation, which describes the spread of a distribution around its mean. We'll learn how to calculate the standard deviation, and we'll learn its important properties. Let's learn about the standard deviation by looking at some data from the Michigan State Laboratory. Here are the levels of one compound found in the urine of 10 people. Let's use the mean to describe the average value found. It's 16.9. That's good to know, but it would also be good to have a numerical way to describe how tightly the data cluster around the mean. As a start, then, let's look at how much each observation differs from the mean. To find that out, we can just subtract the mean, x bar, from each value. As you can see, some of these deviations will always be positive and some will always be negative. In fact, their sum will always be 0, which allows us to check our arithmetic. Now, we can't just average the deviations to get a sense of how large they are. The average would always be 0. To get around that problem, we'll square each deviation. The squares are always positive and are large if the deviation from the mean is large in either direction, positive or negative. Since the squared deviations are all positive, we can find their average to get a reasonable measure of spread. When we do this, however, there's one minor oddity. Instead of adding them up and dividing by the number of deviations, we always divide by one fewer than the number of deviations. The number we get is called the variance, and it is symbolized by s squared. The calculation is summarized by this algebraic recipe. You can see that this formula says to subtract the mean, x bar, from each observation x, square these deviations, add them all up, and finally divide by n minus 1. That's shorthand for the calculations needed to get the variance. There's one problem with using the variance as a measure of spread. Since we squared all the deviations to get it, the variance is measured in units that are squares of the original units. That's confusing. So we just take the square root of the variance to bring us back to the original units. The square root of the variance is called the standard deviation. It's the measure of spread that usually accompanies the mean in describing data. The standard deviation is denoted as s, and in this case it's about 7.5. Calculating s, the standard deviation, is a good way to really understand this important statistic. Doing the work reminds us that s comes from looking at how far the individual data points deviate from the mean. But in practice, x bar and s are usually found with the help of a computer or calculator, which can give these statistics with the push of a button once you've entered the data. Let's see how knowing the standard deviation helped the Michigan researchers. The problem the Michigan doctors faced was quickly reading the data from an analysis of many body compounds. Since the standard deviation was different for the different compounds, it was time-consuming to determine whether a given individual's reading was within the normal range or not. The solution was to use sound to supplement the visual information of the charts. The peaks and valleys of the chart were converted into the notes of a familiar song. If the value was within the normal limits as determined by the standard deviation, the notes together play a familiar tune. But a value out of the normal range plays a sour note.
This has the beautiful feature that the analytical chemist already knows in his or her mind what is normal and can then listen for these abnormalities. One sour note meaning a diagnosis of a particular disease, and a different sour note, diagnosis of some other disease.
Now let's learn to interpret standard deviations. To begin with, we need to realize that S, the standard deviation, is always greater than or equal to 0. That's because it's based on an average of squares, which are all positive. A standard deviation of 0 is only possible if all the data points are exactly the same, meaning there are no deviations from the mean and thus no spread in the data. If the data vary in any way, the standard deviation will be greater than 0, and the larger the spread, the larger the standard deviation. For instance, let's return to our previous data. We found that S for these 10 data points was about 7.5. Now let's look at the values for a different compound, using the same patients. The mean in this case is almost the same as before, 16.2 as opposed to 16.9. But here the spread appears to be smaller, and calculating the standard deviation confirms it. Here S is only 1.9, which is a small deviation indeed, given these units. You'll meet the standard deviation often as you learn more statistics, so let's look at some of its important features. First, S only measures spread about the mean. It should never be used with the median. Second, S is always either 0 or greater than 0. It can never be negative. Finally, remember how the mean could be pulled up by one large observation? The same is true of the standard deviation. A single outlier can raise the standard deviation a great deal, distorting the picture of spread. Now you know two numerical ways to describe the center and spread of a distribution: the 5-number summary and the mean together with the standard deviation. The 5-number summary generally gives a clearer, brief picture of a distribution. In general, you should only use the mean and standard deviation when you know that your distribution is roughly symmetric with no outliers. Despite this restriction, the mean and standard deviation are much more commonly used than the median and 5-number summary. The reason is that many natural phenomena can be described by a particular kind of symmetric distribution called the normal distribution. And for such distributions, the mean and standard deviation are just the right measures of center and spread.